Okay, so goodbye. Today we are going to start with the equilibrium constant expression, or you can say that how we can write down the equilibrium constant expression. So move to the slide number 2. Okay. So first of all, if we talk about the reaction that we have discussed previously, we can write down a reaction between the hydrogen and iodine. So H2 plus I2, it react to form the 2 moles of hydrogen iodide. All the species are found in the gaseous state. So if we talk about the this one reaction, so equilibrium is established in this one reaction. But as we can take different concentrations of the reactants, that is the hydrogen and iodine. So a table is presented to you. So it's saying that in one experiment we have started with this much concentration of hydrogen. We have taken this concentration of iodine and we have got this concentration of the hydrogen iodide. So at the end, they have written a quantity in which they have taken the ratios of all the substances that are involved in the equilibrium. It is about the hydrogen iodide, it's about the hydrogen as well as the iodine. So if we talk about that, what is the speciality of this one ratio? So you can see on the slide that the concentrations of the hydrogen iodine and hydrogen iodide are written in these one square bracket, just like if we talk about the hydrogen, so its concentration is written in the square bracket. So keep in mind that if we talk about that, if any concentration is written within the square bracket, so what does it mean? So this square bracket means that your concentration is given in so concentration given in mole per decimeter cube. So if you are measuring your concentration in the form of mole per decimeter cube, then you would write them with the square brackets. Got it? So this is the literal meaning of writing the concentrations of the species in the square bracket. So it means that all concentrations are taken in the mole per decimeter cube. The second one thing that is important for us, that how this ratio has been written. So you can see on the slide that if we talk about the concentration of hydrogen iodide, so that has a coefficient of the 2. And if we talk about the concentrations of hydrogen and iodine, so they are not having any coefficient, and you know that when there is no coefficient, no power written, so that power is considered to be 1. So can you relate this one coefficients with the balanced chemical equation? Yeah. So basically when you are going to take the ratio of the concentrations of reactants and the products, so it's about the stoichiometry of the balanced chemical equation. That in the balanced chemical equation, if you are considering the 2 moles of the hydrogen iodide, so your ratio of concentrations, it would also contain the concentration of hydrogen iodide raised to the power of 2. If you talk about the iodine and you talk about the hydrogen, so both these are having the coefficient, you can say that it is 1 mole is involved, so that's why the exponent or the power of concentrations in the concentration ratio is also taken to be 1. So you have seen that if you have taken the ratio of the concentrations of hydrogen and hydrogen iodide and iodine, so we have got a value that is taken calculated to be 161. So in the next one condition, you have taken another set of concentrations of hydrogen and iodine. So in the second set of experiment, you have taken this one concentration of hydrogen, iodine, and you have got this concentration of hydrogen iodide. So you can again put all these values in the concentration ratio. And when you have put all these values in the concentration ratio, you have got the value of 159. In the third set of experiment, you have taken different concentration again. So in all these four experiments, you have taken different concentrations for the reactants and you have got the different concentrations of the product. But if you have taken the ratio of the concentrations, so you are almost getting the constant value. And we can say that on average, the ratio of concentrations is coming out to be 160. Got it? Yes. So we can say that on average, we get a value of 160 for ratios of molar concentration. Goodbye, what do you know about the molar concentration? The reason about getting 160 is because the hydrogen iodide have the maximum amount of reaction to produce hydrogen iodide. No, basically the reason for getting the same value of the molar concentrations is about the position of equilibrium. So no matter you are using how much concentration of the reactant, so the as we know that under the same set of conditions, the position of equilibrium always remains same. So because of this, we are getting the same value of the ratios of molar concentrations. Got it? Yes. Yeah. So at same temperature and pressure, as the position of equilibrium always remains the same, no matter what is your initial concentration of reactant or the product, but the you can say that the relative ratios of molar concentration would always remain same. And because of this fact, you are getting the same values for the molar same value for the ratio of molar concentrations. Got it? Yes. So goodbye, keep in mind that this constant value that we have got 160 on average, this is called as the equilibrium constant. Got it? Okay. Okay. So basically this one is the value of the equilibrium constant and this is represented by the symbol Kc. So all these values can be written as the Kc, right? Instead it is equilibrium constant. Why did they write E K instead of E? Sorry? Why did they write K instead of E? Because it is equilibrium constant. No, K is showing you the constant, right? And if we talk about the subscript C, so that is written for the fact that this constant has been obtained by using the molar concentration. You know that the molar concentration is represented by the C, right? So that's why K is representing the constant. And if we talk about the subscript C, so that stands for the fact that you are getting this value by using the molar concentrations. Got it? Yes. Okay, jump to the next one slide. So we can say that Kc, so that is called as the equilibrium constant. Equilibrium constant. and basically this is found to be same because it's a constant value, so it would always be found same at same temperature, right? So always have same value at same temperature. So keep in mind that the value of Kc is only dependent upon the temperature.
Sir, what about pressure or molar concentration? No,
It is not dependent upon the value of molar concentrations. So in such some reactions which are having the marked effect of the pressure, so they can just lead to a change in the position of equilibrium by varying the pressure. So those reactions may be affected by the changes in the pressure, but most of the time the temperature is the major factor that controls this one value, but molar concentration has no effect on the value of the Kc. Got it? So it is.
no, sir. And the value because they will have the same value at the end.
So the reason is that if you are changing the molar concentrations, so the value of product it would also change in the same way, right? So if you are using the little amount of the hydrogen and iodine, so you would get the little amount of the product Hi. But when you would take the ratio would always remain the same. Got it?
Yes.
So independent of the initial concentration of reactants. The value of Kc is not dependent upon the initial concentrations of reactants. So these are the two major important points that are related to the value of the Kc. Okay, so now we want to write down the equilibrium constant expression in a general sense, right? So equilibrium constant expression. Now we are going to write down an equation which would relate the value of the molar concentration of the reactants and the products and the equilibrium constant, right? So we can take example of a hypothetical reaction in which we are using the you can say that suppose we are using the reaction between the A and B. So we say that m moles of a substance A react with the n moles of a substance B, and a reversible reaction takes place. A dynamic equilibrium is established between them, and you get the P moles of the product C, and you are getting the Q moles of the product D. Got it? So if we want to write down the equilibrium constant expression, so equilibrium constant is represented by Kc, and Kc is equal to, goodbye, can you help me to write down the equilibrium constant expression for this one? How we can write down?
Which it will be BC plus QD over MA over MB.
Okay. So goodbye, I have told you that what is present as the coefficient in your equation, that would be made the exponent in the equilibrium constant expression. Okay, so write
Now the
down.
product has to be squared.
No, not the scale. Now in this one form, you are having the P and Q as the coefficients, right? So you would write them as the exponent in the equilibrium constant expression. So look at the slide. So we have a product C. You would write down the square bracket. What is the meaning of square bracket?
Square bracket, it means that, wait, yeah, it means that, oh, it's forgot.
So you have forgot. So I have told you in the previous one slide that the square bracket means that you are taking the concentration in the form of moles per dmq, right? Okay. So you would make the P as the power of your molar concentration, right?
Yes,
Okay. Then goodbye. Keep in mind that many students make the mistake that in the balanced chemical equation, here it is written the plus between the two products. But in the equilibrium constant expression, you should not write down the plus. In the equilibrium constant expression, the molar concentrations of the reactants and the products, they would be multiplied with each other, right? So if you're going to write the expression for the D, so it would be written that you would again put another square bracket. Your product is D and Q is the power of this one molar concentration. Got it? So never
yes,
put plus between the two concentration terms. These are multiplied with each other. Got it? Then you would divide them with the molar concentration of the reactants. So you would write the A would be raised to power what? What would be the power of concentration term A?
it will be rest of the bar.
It would be M.
Mister, from where did you bring this letter?
Sorry?
From where did you bring these letters?
I have
Yes,
just
yes, okay, so B, it will be bracket and this is about it.
I'm just writing the equilibrium constant expression for a hypothetical equation, right? On the next one slide, we would write down the actual equation. Then you would get
Okay,
the original values of the number of moles. Okay, so next one we can write down the reactant B. And goodbye, what is the,
bracket,
sorry?
then it will be rest about N.
Yeah, raised to the power n. So this is the way you can write down the equilibrium constant expression for any reaction. So you should just write down the concentrations of products in the numerator, and you should write down the concentration of reactants in the denominator. Got it?
Yes, I got it.
Yeah. So when you are going to write down the equilibrium constant expression, so this is important that all the concentrations of the products should be written in the numerator, and there should be the multiplication between them, not the plus. They are not added together, they are multiplied together. And any number
Mister,
of,
in the reaction it is plus.
yeah, in the reaction in the balanced chemical equation it would be plus, but in the equilibrium constant expression the concentration terms are multiplied with each other.
Okay,
Yeah. And any number of mole that is present in the balanced chemical equation would be made the power of the concentration terms in the equilibrium constant expression. Got it?
yes.
Okay, good. So goodbye, jump to the next one slide. Now we can write down the equilibrium constant expression for an actual equation. So I'm writing an equation on the slide. So suppose we have got the, okay, suppose we want to write down the equilibrium constant expression for the same reaction we have studied earlier, that the H2 plus I2 reversibly give the 2HI, and all these substances are in the gaseous state. State symbols are important. Okay. So goodbye. Now let me know that if I want to write the Kc expression for this one. So Kc is equal to what? How I can write down the
It's
Kc?
equal to bracket I, bracket HI,
Hmm? Hy
then bracket, close the bracket, then write this 2.
square. Okay.
Yes.
Then
Then bracket H2,
okay. So H2.
another bracket I2.
Very good. Okay. So we can still write another one equation. So N2 in the gaseous state reacts with the 3 moles of hydrogen in the gaseous state to make reversibly 2 moles of ammonia in the gaseous state. Goodbye, help me to write down the Kc expression. First, let me know that this equation is representing which process?
It's representing the Haber process.
Yeah, very good. Excellent. Haber's process for the synthesis of ammonia. Okay. So Kc is equal to, okay. So let me know
It is
the
equal to bracket in H3, the rest is about 2.
very good. Okay, then
Over bracket N2,
hmm,
bracket H2, rest is about of 3.
excellent, excellent, very good. So now you have got the idea that how we can write down the equilibrium constant expression for the various reactions. Very good. So goodbye. One more thing that is very important as far as the concept of equilibrium constant expression is concerned. Move to the next one slide. So we can say that up till now we have considered only those reactions that are involving the gases, right? But if there is a reaction in which any solid species is involved, so we can write down an equation as an example that if the silver ions in the aqueous state they react with the iron 2 Fe plus 2 in the aqueous state, and it reversibly gives you the silver solid. Okay, if I given you the solid silver plus it would give you the second one species which involved in this one reaction is the hmm, let me write down about the second one species. So it would give you hmm, okay, so this one is giving you the iron plus 3. So Fe plus 3 in the aqueous state. But it is said that if you are going to write down the Kc for this one, so you would write in this one manner: Kc equal to concentration of iron plus 3, and it will be divided by the concentration of silver ion and the concentration of
It's a lot about Ag solid origin
yeah.
because it is not reacted.
uh, this one is found in the solid state. So I have told you that while writing the uh, equilibrium constant expression, you would not include the solid substance, whether it is the reactant or the product. So the concentration of solid substance is not included in the equilibrium constant expression, because it is believed that the concentration of solid would remain same whether the action is going in the forward or the reverse direction. So the concentration of solid remains same, so that's why it would not be written in the equilibrium constant expression. Got it?
Yes.
Okay, so we can write down here that concentration of solid species, goodbye, this is not about the species in the biology, right? Species is not included.
Professor, I don't like the chapter which like it identify like human as a species, then it will as groups, then as a kingdom.
Hmm.
As a chapter is so crazy.
Oh, so have you studied that chapter in the biology?
Yes, in the universe because it does not even relate to biology. It is just something environmental.
Okay, but I am just using this one word in order to indicate any substance, right? Just any reactant or the product is not included in Kc expression. So if you get any solid thing, any solid substance, whether it's the reactant or the product, so you would not include the concentration of that substance in the Kc expression. So that's why I was saying you at the start that state symbols are very very important, and whenever you would be given any question in the exams, you would be given the state symbols along with it, because if you are not given the state symbol, then how you would identify that any substance is existing in the solid state, or it is existing in the aqueous or liquid or the gaseous state, right?
But sometimes, like in the question, they mention that a solid is form of precipitate is form. They want to check you.
Yeah, so sometimes they would write on in the explanation that this one substance precipitates. So you know that if any substance is precipitating out, so it would be in the solid state, right? Sometimes they would say that this one substance is deposited on the cathode anode. So you know that this one is deposited, so it is in the solid state. Yeah. The next one thing that we are going to talk here is about the units of the Kc. So jump to the next one slide. It's important when you're going to write the Kc expression. So you should have to write down the units. So units of Kc. So when you're going to write the unit for the Kc, so you should know that what is the unit for each concentration term in the balanced chemical equation. And goodbye, keep in mind that Kc is such a quantity that it may have unit it may not have unit, and it depends upon the stoichiometry of your balanced chemical equation. Got it? So first we would write down about a reaction in which your Kc is having a unit. So we have got this one reaction. So I'm writing the reaction on the slide. So 2SO2, it combines with the O2, and goodbye. What would be the product?
It will be CO3.
2SO3. So all the substances in the gaseous state. Okay. So goodbye. When you are going to write the the units for the Kc, first you should write down the Kc expression, right? Then you can write down the units for Kc. So Kc is equal to the concentration of SO3 raised to power 2 divided by concentrations of SO2 raised to power 2 and concentration of O2, no power. Okay, so goodbye. Can you tell me that what is the unit for each concentration term? So if I ask you that what is the unit for the concentration of SO3, so can you tell me?
So remember the unit symbol.
Sorry?
The unit that should be mole per decimeter cube.
Very good, very good. So I have told you that if you are writing the concentration terms in the square bracket, so it means that you are using the units of the molar concentration, mole per dm cube. So I would write here mole per dm cube and its square, right? So then divided by, again the next one concentration would be given the unit of same mole per dm cube, and I would put the square. The next one is mole per dm cube, and there is no power. Got it?
So
Okay.
after they will cancel each other's
Yeah.
numerator and the denominator.
So we can say that this mole per dm cube square and this, they would be cancelled out with each other.
So the unit will be mole minus 1 decimeter cube.
So it would be 1 upon mole per dm cube. And when this one term would be rearranged, so you would get the per mole
Plus 1.
and
Yeah.
dm cube.
Yes.
So imagine this is the way you can find out the unit for your Kc, right?
Yes.
Very good. Okay, so now jump to the next one slide. We can write down another reaction. Suppose H2 plus I2 reversibly gives you the 2HI. All the substances in the gaseous state, write down the Kc. So you would get the HI
Square.
square, good, divided by H2
I2.
and I2. Okay. So now I want to find out the unit.
So here it will be decimeter more per decimeter cube square.
Very good. It's
Here
here.
it will be mole per decimeter cube
Mm,
over mole per decimeter cube. consideration.
Right. So next one is the mole per dm cube. So now you can see that this one square can be cancelled with these two terms, right?
Yes,
So in this one condition, what is the unit for Kc?
it is just there's no unit.
Yeah, so Kc has no unit. So now goodbye, have a look at the equation. So you can see that in this one chemical reaction, the number of moles of reactant and the product, they are same. So you can see,
Yes,
so you can write about such reactions. So those reactions in which the number of moles of reactants is equal to the number of moles of products, the Kc has no unit. Got it?
yes,
Yeah. So this is the concept that if the number of moles of reactants and the products, they are equal, then there is no unit for the Kc. Got it?
yes. I didn't know that like chemistry have to do like some calculation with math because I like math.
Hmm. So you like the calculations in the chemistry?
Yes,
Yeah, very good. So from this one portion, so this chapter is involving the calculations. The next one is also involving some calculations about the acid and bases. But after
but
that,
Mister
hmm,
in the exam they bring the question as a puzzle. That's why it is so hard.
so sometimes you have to do the calculations in the chemistry, because if you talk about the organic portion, there is no calculation in that. And if you talk about the inorganic portion, so that's also about more about the periodic trends and the complexes and the transition metals. That's also not involving the calculations. Only the physical portion and the analytical portion of the chemistry involves the calculation. Got it?
Yes.
Okay, so goodbye. This was all about our today's class.